What if the quantum synchronization we've been pursuing for decades is fundamentally impossible without the right conditions? For years, physicists believed that atoms could synchronize their light emissions through pure quantum mechanics and create something called a super-radiant state. However, groundbreaking research published in December 2024 revealed a surprising truth. Atoms in open free space cannot achieve true quantum synchronization, no matter how hard we try. This discovery is not just about failed experiments. It concerns understanding the fundamental requirements of collective quantum behavior and has profound implications for the future of quantum technology. Published in PRX Quantum by a team led by Anna Maria Ray from JILA and the National Institute of Standards and Technology, this work challenges decades-old assumptions about how quantum systems behave. Their findings are changing our thinking about quantum synchronization, quantum computing, and the nature of collective quantum states. Let's take a closer look at this extraordinary discovery. To understand what went wrong, or perhaps what went right, we need to start with what physicists expected to happen. In quantum mechanics, identical particles can sometimes behave as a single collective entity, rather than as independent individuals. This phenomenon, called quantum synchronization, occurs when particles coordinate their behavior through quantum entanglement and shared interactions. The most striking example of this is superradiance, predicted by physicist Robert Dicke in 1954. In superradiance, a group of atoms synchronizes light emission so perfectly that it emits light much more intensely than the sum of its parts. This is akin to a stadium full of people saying the same word at the same time and creating a sound wave powerful enough to shake the ground. For decades, superradiance remained theoretical. Then, in the 2000s, physicists achieved it in optical cavities. These cavities are essentially small boxes made of mirrors that trap light, causing photons to bounce back and forth between atoms thousands of times before escaping. This trapping creates a shared electromagnetic environment where atoms constantly exchange information via the trapped photons. Synchronization arises naturally in these structured systems. The cavity acts like a communication network, allowing each atom to sense what the others are doing. Through constant feedback, the atoms align their quantum states and begin to radiate in perfect harmony. The result is superradiance, a true collective quantum state. However, cavities are artificial constructs. They require precision engineering, perfect mirrors, and careful isolation from the environment. What physicists really wanted to know was whether nature supports quantum synchronization without human intervention. Without mirrors, constraints, and structures, could atoms in free space exhibit the same collective behavior? What do you think about this? Recent experiments in Europe seem to suggest that the answer may be yes. Researchers created pencil-shaped, elongated clouds of ultra-cold atoms and directed them with lasers. Under certain conditions, the atom cloud exhibited signs of collective emission resembling superradiance. The atoms appeared to coordinate their light emissions, suggesting that a transition to a synchronized state might be occurring. This generated considerable excitement. If superradiance were possible in free space, it would imply that collective quantum states are not merely a result of clever engineering, but a fundamental property of matter itself. This would open the door to quantum technologies operating in open environments rather than closed laboratories. It would also confirm that quantum mechanics naturally produces order and synchronization without an external structure. Anna Maria Ray and the theory team at JILA decided to investigate whether this interpretation was correct. Instead of simply accepting their experimental observations, they created detailed quantum simulations to model exactly what was happening inside the atom cloud. Their approach was meticulous. They treated each atom as an individual quantum dipole capable of absorbing and emitting photons from both the driving laser and neighboring atoms. This allowed them to track photon-mediated interactions throughout the entire system and observe how coordination developed under different conditions. What they discovered was surprising and definitive. Across a wide range of experimental parameters, laser intensities, atom densities, and spatial configurations, the model held true. Under narrow conditions, limited collective behavior emerged, but the system never fully formed a synchronized quantum state. As parameters changed, coordination weakened rather than stabilizing into coherent superradiance. As laser power increased, atoms did not become more synchronized, they became more independent. What initially appeared to be a phase transition turned out to be a fragile, transient effect produced by weak photon-mediated interactions. These interactions were not strong enough to maintain long-range coherence throughout the system. The discovery was not that synchronization occurred. It was that true synchronization failed. And the reason why is crucial. The fundamental problem is structure, or rather the lack thereof. In an optical cavity, photons are confined. bouncing between mirrors. They create a shared field experienced by every atom. This confinement produces strong, continuous interactions that enable global coordination of the atoms. Information flows continuously throughout the system, enabling feedback and synchronization. In free space, none of this exists. Photons scatter in all directions. Interactions rapidly weaken with distance. There is no global feedback mechanism forcing atoms into coordinated behavior. There is no shared electromagnetic field holding the system together. Photons emitted by one atom may briefly affect its neighbors, but these effects fragment and dissipate before any system-wide coherence emerges. Simulations showed that even when collective effects emerged, they were unstable. Instead of coalescing into a coherent phase, they reverted to independent emissions as conditions changed. This revealed a profound truth. Quantum synchronization is not merely a consequence of particle interactions. It is a consequence of how these interactions are organized in space, time, and geometry. The research team rigorously tested this result. They used numerous modeling approaches, including microscopic quantum dipole models and simplified mean field approximations. While simplified models could reproduce certain features in dilute regimes, they failed as density and energy increased. Even the most complete quantum models could not produce stable synchronization in free space. This established a clear principle. Collective quantum states require structured interaction networks. Consistency cannot be maintained without confinement, feedback, and organized connection geometry. The absence of structure is not a technical limitation that can be overcome with better experiments. It is a physical constraint specific to open quantum systems. This discovery has immediate practical consequences. First, it sets limits for quantum technology development. No matter how strongly driven or carefully prepared, not all quantum systems can support collective behavior. Quantum synchronization requires engineered environments. This is important for quantum computing, quantum communication, and quantum sensing. Technologies based on collective quantum states, entanglement generation, coherent state manipulation, synchronized quantum bit arrays, cannot operate reliably in open environments. They require structure. Cavities, waveguides, photonic crystals, and structured light fields are not optional enhancements. They are necessary conditions for scalable collective quantum behavior. Second, the research guides future experimental designs. Physicists can focus on hybrid platforms that combine free field flexibility with structured photonic environments, rather than forcing synchronization in open systems. These systems can enable controlled interaction networks without completely confining atoms in traditional vacuums. Nanophotonic structures, metasurfaces, and engineered light modes offer promising avenues. Third, this work demonstrates the critical importance of theory-experiment collaboration. The simulations did not contradict experimental observations, they explained them. It was shown that what appeared to be a phase transition was a limited collective effect constrained by the system geometry. Without theoretical analysis, the physical mechanism behind the observations would have remained unclear. Looking ahead, the JILA team acknowledges the limitations of their current methods. At higher densities and stronger couplings, where quantum correlations become more complex, their theoretical tools become ineffective. New approaches will be needed to investigate these regimes. However, the fundamental result is robust. Quantum synchronization in free space is fundamentally limited due to the absence of structure. This research is changing our thinking about quantum systems. Collective behavior is not universal. It is not an inevitable consequence of quantum mechanics. It is a conditional behavior. It depends on the environment, geometry, and interaction architecture. Atoms in free space are not failing to synchronize because the experiments are not good enough. They behave exactly as the fundamental laws of physics predict. The implications extend beyond this particular experiment. Quantum mechanics addresses fundamental questions such as the emergence of order and the relationship between individual particles and collective states. It suggests that quantum technologies will always require careful environmental engineering to achieve the consistency and synchronization demanded by applications. Ultimately, what appears to be a limitation reveals a deeper truth. Quantum mechanics does not guarantee synchronization. It permits synchronization under the right conditions. Understanding these conditions and building systems that provide them is the real challenge for quantum technology. Free space alone is not sufficient. Structure matters, environment matters, and recognizing these constraints is the first step toward building truly functional quantum systems.